This lesson's on thin film interference, and here are the objectives. Thin film interference is the physics behind the phenomena of the colors on soap bubbles and oil slicks. So understanding where those colors come from is the focus of this lesson. And in order to understand that, we need to go back and review a few things first. First, recall that n was the symbol we gave for the index of refraction of a medium, and n was defined as c over v, where c is the speed of light in a vacuum, that's 3 times 10 to the 8 meters per second, and v is the speed of light in the particular medium we're considering, and that's going to change. The speed of light in all substances is not the same, and it's not the same as the speed of light in a vacuum. Remember that if we have a boundary between two media, and we'll call this medium, and we'll give this an index of refraction of n1, and this one an index of refraction of n2, and we'll draw the normal in like that. If n2 is greater than n1, meaning the second medium is more optically dense, it passes light less readily, then light will bend towards the normal. So we'll see something like this, and it was Snell's law that governed this for us. So remember that n, the index of refraction, is a measure of how optically dense the medium is. Now, some things change and some things stay the same about this light as it passes from one medium to the other. The frequency of the light actually stays the same, and we called that the handshake principle. The oscillating electromagnetic wave here causes the oscillating electromagnetic wave here, and so they are matched up in frequency. Again, that's the handshake principle. But the speed and the wavelength of the wave actually both change. Again, the speed of light in a vacuum is not the same as the speed of light in other media, and the wavelength changes to go along with that. The other thing that can change is the phase, and let me show you what I mean by that. This is the PhET waves on a string simulation. You can see the URL here at the top, and I'm going to send a pulse along this string, and I want you to watch what happens to its up-down orientation. Note that here there is a free end. This ring allows the string to travel freely up and down. So I'm going to send a pulse along, and notice that when it hits that free end, it reflects, and it has the same orientation. It is upright just as it was sent before. So I'll do that once more. Again, it reflects upright. Now, if I change that and I make this a fixed end instead, so that now it can't wiggle up and down, when I send a pulse along, notice that it reflects upside down. I'll do that once more. If I send a pulse along to a fixed end, it reflects upside down. So there's a difference in what happens at this end if it's a fixed end or a free end. Now there's an analogy with what's going on here with the light as well. If we go from an optically slower or optically denser medium to a faster medium, in other words, if the index of refraction in the first medium is greater than that in the second, then this second medium acts as if it's a free end. And so like we saw in the simulation, where the wave or the pulse reflected back upright, we see no phase shift. There's no phase shift for the reflected ray, which I haven't drawn in, but I'll draw in shortly. In contrast, if we go from an optically faster medium to a slower medium, in this case n2 is greater than n1, and n2 acts like a fixed end as we saw in the simulation, and just as we saw in the simulation that the pulse reflected upside down, in this case we'd get a phase shift of 180 degrees, or if we're working in radians, pi radians. And just like in the simulation, we were looking at the orientation of the reflected pulse. Here, be careful that the phase shift we're talking about is a phase shift in the reflected ray, not in the transmitted ray. So let's go back up to this diagram to explain what I mean. Here we have an incident ray and a refracted ray. And if we're going from top to bottom, then we're going from a faster medium into a slower medium. N2 is greater than N1, so N2 is slower. So we're going from a faster medium to a slower medium. This boundary here, where we would be going from a faster to a slower medium, is the same as this kind of situation, where we're going from an optically faster to slower medium. Now, I've only drawn right now the refracted ray, but there's also a reflected ray here. And this reflected ray, because again we're going from an optically faster to an optically slower or a less dense to a more dense medium, this ray would have a 180 degree phase shift compared to this transmitted ray. This transmitted ray and the incident ray are in phase, but this one here is going to be out of phase by 180 degrees because of that phenomenon we saw in the simulation. In contrast, if I were to run this the other way, if I were to go that way, and so this is my incident ray, and that is my refracted ray, and so let's get rid of this one for a moment. Now I have a reflected ray that's down here, coming down like this. And in this case, now I have a situation where I'm reflecting off a boundary from a slower to a faster medium, and so in this case there would be no phase shift if I were firing the laser, for example, from the bottom to the top. Okay, so there's the difference, and that's going to become important in our derivation in a moment. To continue with a few of the background concepts that we need to review in order for the thin film interference equations to make sense. Here we've got three equations. This is the one from above. Index of refraction is equal to the speed of light in a vacuum divided by the speed of light in a medium. And here we have two universal wave equations, one for vacuum and one for medium. I'm going to take this equation and divide it by this one. So I have c over v on the left-hand side and frequency times the wavelength in a vacuum divided by frequency times the wavelength in a medium over here. Now remember that the frequency stays the same regardless of medium. It's a characteristic of the wave that's not going to change. So those are the same and can cancel out. And this is equal to n. So I have that the index of refraction n is equal to the wavelength of the wave in vacuum divided by its wavelength in any particular medium. And rearranging this, I can solve for the wavelength in a given medium, and it's just equal to the wavelength in a vacuum, which we often just call lambda without this sub-vac, divided by n. So this now is a way of getting the wavelength of a particular frequency of light in any particular medium once we know its wavelength in vacuum. And we're going to use that in a moment. Alright, now that we've got all that background, we're ready to look at thin film interference. So here in this diagram, I have a region of air, and then we're going to talk about soap bubbles for this, but it would be the same for other things. So this is my soap. This is the thickness of the soap bubble here, and that thickness we're going to call d. And then I've got air inside the bubble as well. And my eye is going to be over here. So here's my eye looking at rays that are coming up. And these are light rays. So I've got light coming in like this, hitting the surface of the soap bubble and reflecting, but also hitting the surface of the soap bubble and being transmitted. And you can see that because soap is bending the light towards the normal, soap is more optically dense than air. Imagine my normal is here. You can see, like the drawing above, the light is bending towards the normal, so soap has a greater index of refraction than air. So this is N2, this is N1, and this is N1 again here. And then the light is coming back up like that. So I've got one ray that's splitting here into a reflected and a transmitted or refracted ray, and then we're following them. These two rays are coming to my eye, and what I see is going to depend on how these two interfere with each other. Now the wavelength of the particular light that I'm looking at here, we're going to call lambda. We're not going to use sub-vacuum. And for our purposes, the wavelength in vacuum and the wavelength in air are effectively the same. Now the wavelength in soap, though, is going to be different. As we've seen, the wavelength in soap is going to be equal to lambda, the wavelength in vacuum, divided by the index of refraction of soap. And because the index of refraction of soap is going to be greater than 1, the wavelength of the light in here in the soap is actually going to be shorter than it was out here in the vacuum. Now we need to think about what's happening at the 2 points of reflection in the diagram, here and here. Here we have a reflection as we're going from a faster medium with a lower value of n to a slower medium. And then here we have a reflection at a boundary between a slower medium to a faster medium, from soap to air. And we need to categorize these into the two forms of reflection that we have above so we know what's going on. Well, when we go from a faster medium and bounce off a boundary that's with a slower medium, this is like a fixed end, and so we've seen that we have a 180 degree phase shift here. In other words, as this light is coming in, the reflected ray has a 180 degree phase shift compared to the incident ray, and also compared to this transmitted ray. In contrast here, this one's like a free end. We're going from a slower to a faster medium, and so there's no phase shift here at all. So we've got two different kinds of setups, and this is particular to the way that this is, that we've got air and then soap and then air, where we've got a lower value of n, then a higher, and then a lower. And if we change these up and, for example, put a different medium here, then we could get another phase shift here, for example. It depends on what the particular media are in your three locations in the diagram. But the way it's set up, if this is boundary 1 and this is boundary 2, we have a 180 degree, or if we want to work in radians, pi radians phase shift at boundary 1, and we have no phase shift at boundary 2. Alright, now let's think about what I'm going to see at my eye. We're going to imagine that we're using red light of wavelength 650 nanometers. So if we shine that red light here, monochromatic red light, it's going to hit this boundary and it's going to split. Some of it's going to be reflected with a 180 degree phase shift, and some of it is going to be transmitted with no phase shift, bounce off this boundary again with no phase shift, and come back towards my eye. So there's two differences between the light that is traveling along here and the light that's traveling along here. This one has undergone a 180 degree phase shift from the start, and this one on the right has undergone no phase shift, but it's traveled farther. And if we look at this triangle and imagine that this triangle is basically just a straight line down and a straight line up, the path difference here is effectively twice the thickness of the film. So the path difference is 2d. Yes, it's a triangle, but imagine collapsing the triangle until it's really narrow and it's effectively going down d and coming back up d. So this one's undergone a 180 degree phase shift, and this one has undergone no phase shift, but has traveled a path difference of 2d, where d is the thickness, farther. In order to see bright red light at my eye, we need constructive interference, and so we need these two effects to cancel each other out. We need this path difference of twice the thickness of the film to bring this ray back in phase with this ray that's undergone a 180 degree phase shift. Putting that into an equation form, let's first think back on our double slit interference formulas. Remember when we wanted constructive interference, we had an integer number of wavelengths was equal to our path difference. D sine theta was our path difference using trigonometry in our diagram, and this was an integer number of wavelengths, and this was for constructive interference. And for destructive interference, we had a number of half wavelengths like this. And this gave us destructive interference. So that's review from an earlier lesson. We're going to use the same kind of thing, but the conditions are going to be reversed. If we want constructive interference here, because we've got this 180 degree phase shift happening in one of the rays, we actually need a number of half wavelengths like this to get us back into phase. So here I'm going to use m instead of n because n is used already for the index of refraction. So we need a number of half wavelengths to get us back into phase, and we said that our path difference is going down and then going back up the film. So 2d has to give us that appropriate path difference to get us back in phase when the 180 degree phase shift got us out of phase. Now this is not quite right yet because we need to talk about the wavelength in the SOAP. So it's equal to lambda over n SOAP. So this is now our equation. 2d is equal to m plus a half lambda over n SOAP, where this is an integer 0, 1, 2, like n was up here, but now the conditions are reversed, so we're not using that same sort of setup. And this over here is the wavelength in the SOAP. In contrast, if we want destructive interference, so a dark band at our eye, we need that path difference of 2d to be equal to an integer number of the wavelength in the SOAP. Now, we've looked at this for 650 nanometer light, so this wavelength would be 650 nanometers, and we'd get a particular thickness that would give us dark bands and a particular thickness that would give us bright red bands. In fact, the equation gives us multiple thicknesses, the thinnest one being where m is equal to 0, then thicker when m is equal to 1, etc. That would be different for green light with a different wavelength, and so we'd get different thicknesses that would give us a bright green band, and for all the other colors. So when we shine white light at a bubble, we see different colors in different places as a result of the different thicknesses and constructive interference happening for different wavelengths of light. And that's how bubbles create those rainbows of colors.